In a complex digital system, every component depends on the architecture surrounding it. If foundational dependencies are mapped incorrectly, the entire structural grid shatters. Information systems support organizational tiers, represented by a three-layered pyramid. At the base, operational-level transaction processing systems handle raw data. The middle knowledge level uses decision support systems for management. The peak strategic level uses executive support systems to guide long-term goals. The gap between these layers is navigated by the systems analyst, translating strategy into operational software. First, they serve as a consultant, advising which business problems actually require a technical solution. Second, they act as a supporting expert, providing the technical knowledge needed to solve those problems. Finally, they are an agent of change, helping employees transition from legacy systems to new ones. Systems analysis is a discipline of structured decision-making, bridging the strategic layer to the operational layer, ensuring every line of code serves a business goal. Before a single line of software is designed, a project must survive a three-pronged feasibility study. This includes technical feasibility, can current technology handle the load, and operational feasibility, will the employees actually use the new interface? But the most quantifiable metric is economic feasibility. The analyst must prove that the projected value of the investment exceeds the time and capital costs. This hand-drawn break-even analysis graph is the tool used to justify massive upfront IT expenditures. The x-axis represents the volume of work or units processed, while the y-axis tracks the total financial cost. The current system cost line shows a lower starting point, but a steeper slope over time, as the old system becomes less efficient at high volumes. The proposed system cost starts significantly higher on the y-axis due to the fixed cost of building the new software. The critical intersection point is the precise moment the efficiency of the new system pays off its initial creation debt. If the organization cannot realistically project reaching this volume of units, the project is killed immediately to prevent waste. Economic feasibility identifies the mathematical threshold where technology justifies the cost of its own development. Once a project is economically validated, the analyst selects the architectural framework used to build it. The traditional approach is the Systems Development Lifecycle, or SDLC. It is a sequential, cascading framework that moves through 7 distinct phases, from identifying problems to testing and final implementation. Analysts choose SDLC for massive, complex systems, where management requires predictability and exhaustive documentation. The weakness of SDLC is its rigidity. It is vulnerable to failure if the business requirements change during a long development process. Agile development is the modern, dynamic alternative designed to handle that vulnerability. This flowchart represents the cyclic, agile project development process, where exploration and planning feed into rapid iterations. Software is released in basic versions called small chunks, allowing the team to test and improve the code incrementally. Agile is the correct choice for applications that must be developed rapidly in dynamic environments or during the emergency rescue of a failing system. One methodology is a linear march toward a finished product. The other is a continuous loop of adaptation. The choice is dictated strictly by the project's requirement for documentation versus its demand for speed. The final vector of the decision matrix is determining where the software will live and who will maintain it. The top row of this table outlines the trade-offs of creating custom software completely in-house. Custom builds provide specific responses to business needs, but they carry a massive initial cost and a permanent maintenance burden. When we zoom out, feasibility, methodology, and infrastructure form a single interconnected systems decision matrix. Consider Scenario A, architecting a university results system. The requirements include high security, static mathematical rules for grades, and zero tolerance for errors on live users. The optimal path through the matrix connects high-control local hardware with the rigid, highly documented SDLC methodology. Scenario B is the architecture for a modern online shopping system. This requires rapid deployment of new features, handling fluctuating user traffic, and a seamless interface. This path leads to scalable cloud infrastructure paired with agile iterative development. Choosing the wrong path, like applying a rigid SDLC to a volatile startup app, causes the system to collapse under its own weight before launch. The systems analyst aligns business logic with technical architecture, identifying and neutralizing architectural flaws before they can manifest as software failures.